The real question that I've been interested in over the last while is really what happens when that forest experiences a wildfire, and how does that influence the emissions portfolio off that fire, and also how does that alter what happens with that forested ecosystem going forward as it experiences more climate change. So I'm going to start with a quick primer on the Sierra Nevada forest, since we're clearly not in California. There's far less human biomass here in BC than there is in the state of California. So we're talking about a pretty tall mountain range. Basically goes from the low side, roughly, 500 feet elevation up to about 14,000 feet in the highest peaks. We start with grasslands and end up with tundra, alpine tundra. Precipitation goes up and temperature goes down as you go up in elevation. And I only bring this to your attention so we can talk about it in the context of things burning. So generally when we're talking about these ecosystems, we're really talking about more fuel-limited systems at the lowest elevations. So when productivity is low, the place can't burn every year, right? Grasslands, obviously. So you move into oak woodland and oak pine forest, if you experience a fire, that area will not be able to burn again for several years until you get enough regrowth. As we move up in elevation, we transition to more climate limited. So there's plenty of fuel available, but the period of time throughout the year that it's available to burn because of temperature and moisture is relatively limited. And so once we get up in, say, the spruce fir or subalpine forest, it's maybe 1 in 100 or 1 in 150 years on average where it's available to burn. And so we can think about this in terms of fire return interval. So in the lower elevation forests, it's only a function of productivity. So we can see fires as frequent as 1 to 2 years in the oak woodland, and that's because it's a grass-driven system for fuels. And then when we get in the mid-elevation forests like pine and mixed conifer, where I've done most of my empirical work in the field, we're talking about, say, 10 to 15 years for the fire return intervals, maybe as much as 20. And then up at, like I mentioned, in the spruce and fir and subalpine forest, it's 100 plus years. And so from a biomass perspective or a carbon perspective, we see that the real sweet spot in these systems is really at this mixed conifer pine area. And that has to do with the fact that you've got a long growing season, but you've also above the snow line in the system. So you've got that snow water storage because these are seasonally dry all summer long. And so this is a really super productive, almost like coastal northwestern forest in terms of per unit area productivity, but with a punctuated dry period that basically lasts from the timing of snowmelt in the spring until, say, October or so when the first winter storms come in. And that's where we see the highest both productivity and also carbon storage. So to give you an idea of how I like to think about these ecosystems, forest ecosystems, it's really in the context of this idea of a carbon carrying capacity. So this is the idea that there's a certain amount of biomass or carbon that a particular forest type will carry. And it's a function of the prevailing climate and natural disturbance conditions at that location. And if we have, say, a wildfire occur, and I've got a little lodgepole pine there in the background with about 140, 150 year return interval, and we have the same climate space and the same natural disturbance regimes, we expect that over the course of succession, we resequester all the carbon that was lost from that system due to disturbance. The real challenge comes into play when we start thinking about changing climate or changing disturbance regimes. And this is something that's not uncommon in my neck of the woods, where we're seeing type conversion happen, where a forest burns under high severity fire conditions, and what we have afterward is a shrubland or grassland. And that can equate into a much lower carbon state. So the carbon carrying capacity of that system has come down considerably in the absence of tree regeneration. All right, so you saw this equation earlier from the gentleman that dealt with risk management. So I like to also think about carbon in this context, where we've got, in terms of fire, we've got what's the probabilities relevant to fire. There's a probability that you get an ignition, right? And then whether or not that turns into a wildfire is also dependent on fuels, topography, weather, and those sorts of things. Now, the carbon side comes in terms of consequences. So we've got biomass consumed, tree mortality, and post-fire succession. And the post-fire succession aspect is really important as the climate space changes. So we saw some talks earlier this morning about the doom and gloom future for this region. And I can tell you, I live on the kind of the leading edge of climate change for Western North America, in that we're seeing stuff that I wouldn't have expected to happen for another 10 or I was hoping. It would hold out to like 2050, I'd be dead and it wouldn't really matter to me anymore. But we're seeing some pretty dramatic changes occur in the southwestern U.S. And so that post-fire succession element's really important when we think about climate change. So all of this, right, the changing climate, increasing drought frequency, higher temperatures, in a lot of the western U.S., so particularly in the more frequent fire forests, is happening in the context of, as John Bailey was saying earlier, these overstock stands from fire exclusion. So we're carrying far more carbon in these systems than would be carried under a prevailing natural disturbance condition. And so as a result, fire suppression in the western U.S. has really acted as a selection pressure in evolutionary terms for larger, hotter, tree-killing wildfires. All right, so in a carbon context, you can think about this. Disturbance, if you've got a more frequent fire system, that's the one in the back here, and you're getting regular burns occurring, you oscillate around some stable amount of carbon, quote unquote, right? And so you have these frequent surface fires occur, trees die, a little bit of stuff burns up, but all in all, most of the trees live and they continue to take up carbon. And then in the front of this figure is what I've called the unstable state here, is basically when we have excluded fire from these ecosystems, we've pushed the amount of biomass past the carrying capacity given regular fire occurrence, and we start to see oscillations in the system. And this is, you might raise your eyebrow because when it burns over, not all the carbon goes in the atmosphere. This is really focused on live tree carbon here. All right, so decadal wildfire is increasing, right? So over the last 40 years, some work by my colleague Leroy Westerling looking at area burned in the western U.S. has shown this marked decadal uptick in the area burned by large, greater than 400 hectare wildfires. In the Sierra Nevada, 274% increase in area burned over the last 40 years. The Southwest, 462%. So we're seeing a lot more interaction of fire and forested land area, and this is driven a lot by changing climate. And Leroy's work shows that basically as we've turned the temperature up, we've increased the length of fire season because the snow's melting out earlier, and then we've got more, a larger part of the year that's available to burn. And that's problematic from a carbon perspective, of course. And then we're also modifying the the fire triangle, right? So ignition, weather, fuel. So this is a graph of colleague of mine, Jennifer Balch at CU Boulder, looking at the frequency of human ignitions in red versus lightning ignitions in blue. Across most of the U.S., we've expanded the niche for fire by adding human ignition sources in high frequency. Same time, as temperature has gone up, these systems are drying out, right? So fuel aridity, or a decrease in fuel moisture, has increased. And that has to do with the fact that we're turning the temperature up. And some work by John Abatzaglau and Park Williams has demonstrated that over the last 20 years or so, 50% of the drying that we're seeing is attributable to human-caused climate change. All right, so assuming I got these numbers at the bottom correct, because I came to Canada, I had to convert to Celsius, and usually when I'm talking to forest managers in the US, if I put Celsius up, anyway, The future for the southwestern U.S., for California, is really a hotter and drier one. As was mentioned earlier, as the temperature goes up, precipitation, it was Mike mentioned it, has to go up a lot to make up for the additional atmospheric water demand. So how much water a warmer atmosphere is demanding from the ecosystem. So even if we see winter precip go up, as these model ensembles would suggest for part of the Southwest, it's really irrelevant because it's not going to go up enough to compensate for the increased warming. And so this overall drying pattern, particularly in fire season, is going to make these ecosystems more flammable going forward. And this presents a challenge when we're thinking about the role, as Karen just mentioned, that forests play in helping to regulate the climate. So one of the things that we've been trying to understand is how forest management, which decreases carbon stocks and puts carbon into the atmosphere from burning, plays out over time when we account for a changing climate and also the increasing probability of large wildfires occurring. And so the two questions I want to address for you this evening are based on a number of studies we've been doing. The first bit we'll talk about is the influence of climate and climate-driven increases in area burned on carbon dynamics for the entire Sierra Nevada. And then the next bit we'll talk about what happens when we start to look at managing for reducing the risk of stand replacing wildfire in the Sierra. So all of these simulations leverage a same modeling framework. It's an ecosystem model coupled to a forest demographics model, and we use the Canadian Fire Behavior and Prediction System for modeling wildfire. We've driven them with climate projections from 3 different global climate models, and then we've calculated or estimated fire size distributions based on those climate projections, and so we draw from those distributions to get our fire sizes. So you're going to see a series of graphs like this here, where on the left is baseline climate and wildfire, so that's the last 20 years of climate or so, and then projected climate and wildfire. And these are both run out through the end of 2100. So the only difference being on the left, we've held climate stable and we've kept area burn distributions the same. And on the right, we've allowed those to change. And then these maps show the dominant species by above ground biomass in each of those 12-kilometer grid cells. What do you see when you look at these graphs? If you squint really close, look really close, you'll see that there's not much difference. And that's because fire is still really rare on the landscape, right, even as the probability increases. What you do see, though, is that if we look at above ground carbon, and I've got these binned such that this is